Okay, thank you. Well, today this is a workshop, so not only I have to do some work, but I would also like you to do some work. So I guess you must fall asleep now by the end of the conference, but I will try to keep you awake. And so what I will do is I will try to show you how cognitive flow theory can be used to design environments for complex learning tasks. And I'm gonna do this based on aspects I already presented during my keynote. So I hope that you will remember them, but I will also refresh your memory a little bit. And I first would like to start with a tool we made, and so I would like to ask you to focus on one card and pick this card and then keep it in mind. Try to keep it in your mind. Okay. No. Okay. So, if you thought hard, then probably the card that you had in mind is not present anymore. So, if that worked, then our system works very well. Of course, this is something that if you do it with the whole group, it's clear that this cannot happen. But like it should show how our cognitive system works. That if we focus attention on some aspect, or consciously attention on some aspect in a task, then we ignore the other aspects, and that is what people, what they do in media, but also politicians are very good in this. Like they try to focus your attention on something so that you don't see the other things. And so they use our cognitive system, like I showed you, like the cognitive model. Maybe you can remember it. So we have the sensory memory, and in this memory we try to ignore the information that is not relevant for our learning. And of course this works quite well, but you also know that some information will always come through, because it's very difficult to suppress this information. So our working memory was the most important component for cognitive flow theory, because it's limited in capacity and also in duration. And so this is the main aspect we look at in cognitive flow theory, because we also focus mostly on the early process of learning. So if people don't have schemas yet about a topic, and when they start working in a new domain. And today I'm also, and I showed that also during my keynote, we also look at like educational programs, but the main focus has been on learning tasks. And so the focus on learning environments is rather new, and this will be something I will talk about now. So maybe also to refresh your memory, what we distinguish is intrinsic cognitive load, the intrinsic complexity of the task, which consists of the elements that are in the learning task, and the load imposed by the way in which we present the information, which is called extrinsic, and this can be relevant for the learning, that is germane, and if it's not relevant, we call it extraneous load. And what we typically try to do is going from this situation in which a learning task consists of irrelevant and relevant information to a situation in which we only use relevant information. And of course, that's not always possible, but this is the ideal situation in which we use the whole capacity of our working memory for relevant aspects of the learning task. I also discussed ways to measure mental effort or cognitive load, and so we, today for the workshop, this measurement is most important. So it's a subjective measurement in which we ask the students to indicate how much mental effort they had to invest in studying or solving, studying a task or solving a problem. And this can be done on a scale from 1 to 9 in this case. I also showed the techniques that we used, and this is important for your first task to know how they contribute to the amount of guidance that we can give to students. So we have seen the worked example effect. So according to the worked example effect, you should present students with the problem and the worked out solution. And so in this case, the worked examples provide a lot of guidance and can provide full guidance. And it's also why we distinguish between two types of worked out example. One in which we provide full guidance, which are so-called process-based worked out examples, in which we show what needs to be done, all the steps that need to be taken, but also why you need to take these steps. So this provides full guidance to the students. And then we have product-based worked out examples, which provide less guidance, but still a lot of guidance. They only show the steps that need to be taken and not why. Then we have the completion effect, which are partly worked out examples in which the learner has to fill in some steps, and this can be so that this is sometimes more motivating, because like if you ask students to study things, it's difficult to check whether they actually do it. But with completion examples, we have some check whether they actually study the examples, because they have to complete steps. And you can also imagine that here you can also vary the amount of guidance in many ways, because you can ask them to fill in only one step of the whole solution, which then you still have a lot of guidance. But when you increase the number of steps they have to fill in, then the amount of guidance decreases. And of course, at the end of a training program or an educational program, you want the students to be able to solve the whole problem. And so at the end, they need to be able to solve a problem. So without any solution. I talked about the split attention effect, but that's now not really relevant. We also have techniques for increasing the load that is the good load, so the load that is relevant for the learning process. So this adds load to the learning process, but it has a positive effect on learning. And we distinguish between self-explanation, so we can ask students to self-explain what they did or when they studied a solution, or we can ask them to imagine, to close their eyes and imagine what they did during solving or learning a problem. And both techniques, it's clear that they add an additional load, but research has clearly shown that this load has a positive effect on learning, and especially also transfer of learning. So students who use these techniques are better able to solve problems that are different from the ones they did during practice. So I also talked about the 3 principles, and these are important now to keep in mind. So the first step we always take is look at, we distinguish between different levels of complexity of a learning task. And we sequence then the task from low to high complexity. So students start with a low complexity task, low complexity tasks, and then they go on to medium complexity, and finally they will end up with the highest complexity tasks. Within these complexity levels, we manage the guidance that we provide. So typically you will start with full guidance and then finally end up with no guidance, and during this trajectory the guidance will be decreased. And also they already talk about the personalization principle, which means that we can adapt the learning tasks to individual learner characteristics. And so we can have fixed sequence learning tasks. So if you are a teacher and you have to create a learning program, then you can design learning tasks and you can use a fixed sequence, and that's what we going to do, what I want to ask you to do. But we can also make an adaptive sequence. That will be the second assignment. But for now, I would like to ask you to try to sequence the tasks that are listed here in a logical sequence. And of course, this can be done according to cognitive flow theory. That's what I think is best. But if you have your own strategy or own idea about an effective sequence, then I'm also happy to hear that. So maybe you can work on that in each table in the group, and then I will ask some of you to tell me what the optimal sequence would be. Is that okay for you? 10 minutes? And if it's not clear to you what to do, then just let me know. Maybe to give some, like there is also mentioned a conventional problem. Conventional problems are problems that you have to solve. So goal-specific problems that you have to solve. So are you ready with an order? So who would like to go first? Okay, yeah.
Thank you so much for presenting such a exercise with a high cognitive load.
Yeah.
What we felt was that the way that the problem was presented increased the complexity of the task, and that if it was presented visually, it would be easier for us to solve. It would be easier for us to solve if it was presented visually. But what we've done, so we're critiquing it.
Yeah, okay, yeah.
I'm speaking on the behalf of all the participants here, going first. Seriously, what we saw was the different variables with a type of problem. There was completion, and there was a conventional problem. There was the different types of complexity, which was low, medium, and high. And there were different types of examples, which was a worked example, which could be process or product. So in other words, what we did is sorted it out into the various dimensions and the various factors of the problem that you wanted us to solve. And what we would do, if we were going to put it in order, would go from the simplest through to the most complex, which, looking at all those examples, would probably be conventional, low complexity. Worked example would be from process to product.
What would be the first problem you would start with?
We'd start with the simplest.
Yeah, the simple, and then with what type of problem?
The type of problem, we've got the choice of completion or conventional. So we'd probably do the completion because, well, they're actually cross-secting sort of problems. The type of problem, probably conventional, but then under conventional, there'd be a completion task first.
Okay, yeah.
I think I've just not answered the question properly, but nonetheless, what I'm trying to say is we'd work from the simplest to the most complex. But I think presenting the information in this sort of manner makes it very difficult to sort out what the actual order would be.
Yeah, sure, but if you understand the principles, it is possible to make
Absolutely. Low complexity, definitely, because that's the simplest. Yep.
Yeah, no, of course you will start with the complexity, so you will start with the simplest problem.
Absolutely.
With the simplest class of problems, and,
yes.
And then within within these simple problems, you will start with highest guidance.
Yes.
And so a completion problem and the conventional problem are not the highest guidance, because the worked out examples present the highest guidance.
We had the worked examples over, with those worked examples though, there was a process one and a product one. Sorry, I don't think I was very successful with that, but I understand what you're saying, and I think you're absolutely right in terms of you go from the simplest right through to the most complex.
Yeah, well, I will explain it again. Like based on the principles of the theory, you would start with the, as you said, with the lowest complexity problems. But within these problems, you start with the highest guidance, and the highest guidance is presented by process-based worked-out examples, because they show you what the solution is, and also why you have to take the steps that are shown. So that they present all the information that you need to solve a problem, and you only have to study it. So that is full guidance. And then a next problem, in the next problem you would present a product-based worked-out example, which only presents the steps, and then it doesn't present the why the steps need to be taken. That's something you learn in the first part. So in this case, you would start with a process-based worked example of low complexity, and then you could use a process-based worked-out example with low complexity and add a bit more cognitive load by asking so they could read the example and try to understand it, and then you ask them to explain what actually happens in the example. Then you go on to a product-based worked-out example, which presents a bit less guidance, and also there you can add in a second step, in a second example, you can present again a strategy that imposes more germane load, self-explaining. Then you go on to worked-out examples that are not fully worked out, which are completion problems, and you ask the student to fill in a certain step of the workout of the completion problem. And of course this should also be the low complexity. Then you can have a completion problem and add again some more load by, for instance, asking the students to imagine what they did, the imagination effect, which adds extra load but has a positive effect on learning. And finally, the last step, always in each sequence, will be a conventional problem, because these are the problems that students have to actually solve on a test.
Hello, sorry.
Okay.
Over here.
Yeah, hi.
Thank you, Prof. So I was wondering about the separating them into different levels of complexity. Would you use a taxonomy to do that, or would you, if you have other factors that you know about your examples or your problems, would you bring that into it? So, for example, if you had item response data on a particular item, would that factor into that categorization? What would you typically use to measure the complexity before doing the categorization?
Yeah, according to, well, we follow cognitive flow theory, and so the complexity of a task is determined by the number of interactive information elements in a task. And so you can imagine that there are elements in a learning task, but the elements can also interact and refer to each other. So you look at the number of interacting information elements, and we have a method to count them. And so the lowest complexity tasks are the ones with the least number of interactive information elements, and so the highest complexity with the most information elements. If you want to read more on that, we have published an article on that recently also, in which the method is described in Educational Psychology Review.
Yeah. We follow this traditional method of teaching. So when we follow a traditional method of teaching, generally we don't start with the process. Whereas in an inquiry-based teaching, we start with the product. So, I mean, how that matches with this? This is a confusion yesterday also I think I had discussed with you. So
Yeah.
how to go about this?
Yeah, in many programs you would start with asking students to solve the problem, actually, to do some maybe simple problems and solve them. But like we think, and research has also convincingly shown that if you have no prior knowledge, so you have no knowledge about the task in your long-term memory, then you won't be able to solve the problem, or you use a very ineffective strategy. I showed that in the keynote, like if you have to solve a problem, then you use a backward working strategy, also called means-ends analysis, which will lead you to solve the problem. So you will be able to solve the problem, but you don't learn about the underlying structure of the problem. So that's why we first present the knowledge to the student as much as possible in the beginning, and then only after they have this knowledge in their long-term memory, they are able to work with the knowledge and actually apply the knowledge. And well, the research shows that this way of working leads to better knowledge acquisition, and also for a longer duration, and especially also it enables students to transfer the knowledge that they have acquired, so they can apply it to new tasks.
Thank you. My second query is chemistry curriculum. If we see, it is a spiral curriculum. So spiral curriculum is like, if you don't learn what in one grade, so you can't understand what is in the next grade. So it is a spiral curriculum. Would the sequence work same for spiral curriculum as well as linear curriculum?
Could you please repeat that, because I couldn't understand?
See, if we take chemistry as a subject, chemistry curriculum is a spiral curriculum. Spiral is like it builds on every grade when you go, like grade 6 to grade 7, grade 7 to grade 8. So it goes all the way up to higher education. So it's a spiral curriculum. If you don't understand basic, you won't understand at a higher level. Whereas if you see some other language, it might be a linear curriculum, say physics, light, sound. So the curriculum is completely different. Whereas chemistry is, it builds on each other. Now my question is that would this sequence work for both type of curriculum?
So what are the both types of curriculum? Yeah, because that's difficult to understand for me.
Spiral, linear curriculum versus spiral curriculum.
Spiral curriculum.
Spiral, yeah.
And what does that mean?
A spiral means if I don't study well in grade 6, I won't be able to do well in grade 7. So it keeps on building. The concepts are built on each other. So that's called a spiral curriculum. It goes as a spiral. Whereas linear curriculum is that there are different, areas. I don't know. Someone with curriculum, expertise, please explain. Yeah. Yeah.
Okay. Yeah.
So she wants to know. So if let me take for example the high school, right? So that's where they do physics for grade 10. So it's difficult for you to proceed in grade 11 if you don't have a good background knowledge from grade 10. So your knowledge from grade 10, you use it in grade 11 and you use it in grade 12, you're building on it. So will this also apply for that kind of spiral curriculum?
Yeah, I think there's always you always have some knowledge in your long-term memory. So it's not empty for a certain task. You always have some knowledge. And of course, you can also use that in this method. You actually, well, you should use it. But what are this is mainly to learn the new things that you have to learn. So, but you can still in the practices that you present to the students build on the prior knowledge that they have. So you can expect them to use that knowledge in these examples. Yeah. Okay. Yeah.
Prof? Yeah, I'm trying to understand actually when it comes to teaching and learning, specifically for learners in lower education levels, basic education, where when one is busy teaching, you have to assess the learner's prior knowledge. What is that they know already that can be linked with whatever I'm supposed to teach them as an educator? So I'm looking at the structure that you have put together there, starting with the process-based worked examples that you start by giving them different examples that maybe they start to look based on their complexities, will it not affect whatever they already know, looking back into whatever they're supposed to learn on a particular day? Because if we start back by assessing their prior knowledge, it simply means that whenever I start to provide them with the process-based worked examples, they will be able to link them together. That if we immediately move into the same level without them, without checking what is it that they already have, won't it have challenges for them to acquire the content that they're supposed to learn?
Maybe anyone repeat the question, or like it is? Yeah, it's very difficult for me to understand here. Yeah.
Yeah, I'm asking whether, starting from the process-based worked examples, without even assessing their prior knowledge, what is this? Because to understand that Elena, inside the classroom, did not come in as an empty tin or whatever. This learner will have something. If I'm a teacher who has planned my lesson properly, I'll be able to go deeper to assess whether they have any clue, any understanding, so that even when I start with my lesson, I will be able to identify the diversity inside my classroom. How should I approach it? Even the very same process-based, when it steps in, it will be able to assist these learners to understand this is connected with this one and this is connected with that, so that they understand better. So if we move directly into the process-based example, without even assessing their prior knowledge, won't it affect their understanding of the content? Because if I just come in and start giving them examples, these are the examples that I wanted you to work on, and according to their complexities, so that they should be able to think on their own, without even assessing their prior knowledge, won't it have an effect on the way they're supposed to learn?
So is your question how we can use their prior knowledge in the process-oriented worked out examples?
Yes.
Yeah. Yeah, of course, like in every instructional design, I think you would start with a task analysis, and in this task analysis you also consider the prior knowledge students have. And of course, if you work with a fixed sequence, then you need to rely on what you know from that they did in their previous lessons. So that is your basis for the information you will present in the process-based worked examples. And only if you work with an adaptive sequence, then you can you can better accommodate differences in prior knowledge. In this case, it's like in every class you present the same problems. So it's a fixed sequence, and of course we will take prior knowledge into account, but it's prior knowledge at an average level, what you expect students to have.
Thank you.
Yes.
Thanks so much, and I understand exactly what you're coming from, with all of this. But this would not be the only thing that's happening in the classroom, would it? I mean, the teacher would be, these are just sort of steps for introducing how to solve a problem. There's like introducing the theory, and there's all sorts of other things, and that would include perhaps assessing prior knowledge, when this teacher comes in. So this is built in about, as I'm understanding it, it's all about problem solving in this case. But there's other things that would happen in the classroom alongside that, where the prior knowledge would be kind of assessed and understood in order to work out what sort of examples you're going to do. Is that correct?
Do you mean that a teacher after each example will look at what students actually know, and then maybe adapt the instruction based on that?
Yeah, of course. I mean, what I'm trying to say is that this is not the only thing that's going to happen in the classroom, those examples there. There's going to be a lot of other things.
Yeah, that's true. Yeah, so
yes.
So this is of course a theoretical a theoretically based sequence.
Yes, exactly.
And, yeah.
But there's a lot of other things happening around that. This
Sure,
is just,
yeah,
yes.
yeah, yeah,
So
sure.
with the prior knowledge, which I think is a really good
Yeah.
question, that builds into the spiral knowledge, you know, sort of question that you were coming from, is that of course at all times the teacher needs to assess where the students are at, but this is a sequence of building up their knowledge within
Sure,
a
yeah,
particular
yeah.
topic.
Yeah.
I just wanted to clarify that in relation
Yeah,
to
no,
the...
no, that's yeah, of course that's true. Yeah, so yeah, so this is a theoretical fixed sequence, and of course every teacher would probably intervene if he or she sees that the student has already prior knowledge or works very for who it is very easy. So yeah, that's,
Yeah, thank you so much.
Yeah.
Hello, Prof. Hi, I'm just curious on, is there a specific formula of the timing of these different activities? Because I'm thinking if I'm relating it to my physics lessons, I think it will take me a longer time to implement all of these things. So will timing be important in implementing this aspect? For example, how many, like the number of days that I do this before I proceed to the next step.
So you mean whether the sequence or the problems you choose, whether there's a formula for that?
I'm thinking of, is there a right timing for every process?
Okay. Yeah, the right timing is, of course, in a theoretical sequence, it's difficult to indicate what the right timing is, but of course a teacher will see what the right timing is for an individual student. But if you have a large group of students, then it's very difficult for a teacher, and that's why they normally present tasks in a fixed sequence. And if you use, for instance, like the technologically supported instruction, you are able to adapt to the student, and in that case, then yeah, you could build in, like I will show in the next slide, you can build in some criteria that indicate whether a student has understood the problem and which problem should be given next to the student. Okay, maybe we go on to the next task, otherwise we will. Okay. Yeah.
Professor, could you please explain or define what is meant by conventional problem for us? What do you mean by a conventional problem? So we got a bit confused with that. And also, could you please elaborate this particular process through a very simple example, maybe? Thank you.
Yeah, like I said, I forgot to say what a conventional example is, but a conventional example to us is like a goal-specific problem that students have to solve. Like if you have a physics problem, you ask them, you give them the basic information, and then you ask them, for instance, how far, or what is the distance the car has driven. And so that's the problem that you would get on a test. And we call this conventional problems within cognitive flow theory, because these are the problems that the learning books and the teachers normally start with very soon during the instruction. And what was the other question? So, should I explain other formats? Or the example, yeah. In the product-based work examples, that is actually an example that I showed, I think, in the previous ones. Like here you can see two examples where they are quite complex, but what you see is that in a process-based work, that example, the steps to solve a problem are shown, and also it is explained why the steps are taken. And in the product-based example, only the steps are shown. So that's this is an example of learning materials in physics. And a completion problem would look like, I didn't show it. So this would be a completion problem, which is a worked out example in which you have to fill in certain steps in the solution that you are asked to study. Yeah, so this would be the solution, but I think the main principle is clear. So you start with complexity from lowest to highest, and then go from within each task class from high guidance to no guidance. So if you want to read about this method, then you can also find it in books. It's called the 4CID instructional design model, or 10 steps to complex instructional design, and it was first presented by Jeroen van Marienboer in a book. So in this method, you find all the steps that you can take to design a full instructional program based on cognitive load theory. Okay. So the next assignment, well, we will do it on the spot, and so of course we also can have adaptive sequencing in which we take the individual differences of the learner into account. And of course a teacher will do that if it's possible, and that can be done. The simplest way to do this is by looking at the performance of a student on a task. So if a student has worked, for instance, on a worked example, you can see here, and there is a performance you can have from 0 to 10, and there is a performance of 8, then the next task, so there's a high performance, so the next task could be provide less guidance, because the student is very well able to solve this problem. So probably the next problem could be a completion problem, or it could even go further because it's very high performance. So and like student 3 has studied the worked out example, and there is a performance of 2, which is very low. So you would probably give the student more guidance. So you might give them a process-based worked out example, which provides full guidance, or you present a similar worked out example again and see if that leads to an increase in performance. What we typically do in our adaptive learning environments is we not only use performance, because that is not that informative, but we also look at like the cognitive load imposed, like the amount of mental effort that students had to invest, and then if you do that, then you can get microphone. So as you can see now, for instance, the first student had a performance of 8 and a mental effort of 8 on a 9-point scale. So that means very high performance, but also very high cognitive load. So what type of task would you, or what would you do in your instruction for a next task that you would present to this student? Does anyone have an idea? You are laughing. No. A free goal task? No, that would not be good, because the free goal, or a free goal task, that would go too far, because the student would still have to solve the problem already, and a worked out example is the step from a worked out example to solving a problem is really a big step. Yeah. Yeah. Does anyone else have an idea?
Conventional complexity high.
No, that would be too soon, because like the student has high performance, but also had to invest a lot of mental effort. So it means that it's still quite challenging for the student to work on this problem.
The mental effort 8 means more faster, right?
What is it?
The rating I got confused now.
So a 8 on the mental effort scale means that someone has to invest a lot of effort, almost maximum
Oh.
effort.
Oh, okay, okay,
Yeah.
okay, okay.
Yeah,
Okay, then my answer is for the second student.
yeah. Yeah, so for this student, you would probably maybe present the student with a similar problem, because he is able to solve it, but it still is challenging. So you could stay with the same problem. Whereas if you look at the second student, student 2, who also has a high performance, but this student is able to solve the problem very well with only very little mental effort. It's very easy for this student. So for this student, you would you would make the problem, you present less guidance, or maybe make the problem more complex.
Sorry, Prof. Sorry to interrupt.
Okay.
I was wondering, because typically in adaptive assessment, we start at a point where there's a way to go back and forward. So would that only in this approach apply to how much guidance is provided, or would you start, say, with problems in the medium complexity in various ranges of guidance, and then based on performance there, either move back to low complexity? So both guidance and
Yeah.
complexity is
Yeah.
addressed.
Yeah, both sides would be possible. So if you just started working in the second complexity level, then of course if you see that someone has low performance with very high effort, then you would probably go back to the previous complexity level and try to see whether it is possible to give the students more of the first complexity with very low guidance, and so you would go back then also. Yeah.
Thank you.
Okay, and it's also clear that if you only look at performance, you would not catch the difference between students. So the amount of mental effort, the effort that students have to invest, is really a measure that can be used to give a more fine-grained instructional support to the student. So and the other student 3, for instance, has a very low performance with very high effort. So that means that we should probably go back maybe in complexity level, or we need to present more guidance for this problem. So what about the last student? What is happening there? Does anyone have an idea?
Motivation is required. I said motivation is more required.
Exactly, yeah. That is probably a motivation problem. So if you have very low performance but also very low effort, then it means that you didn't work hard, and of course you had low performance. So for this student, it is difficult for cognitive flow theory to generate rules, but of course you could present this student maybe with a more challenging task that would challenge the student more, maybe a different topic, use a different topic in the task. But yeah, so this is not cognitive load, but motivation. So we also developed a method in which we combine performance and mental effort, so that you can use in an adaptive learning system. So this is based on the effort that the student invests and the performance they achieve. And the idea is that if you can present it also visually, like here, that if a student have high performance with a low mental effort, that means that the schema that the student has acquired is very efficient. So you can achieve high performance with only little effort. On the other hand, On the other hand, if you have to invest a lot of effort and you have low performance, then that means that your schema was not efficient. And so based on all the points in this cross of axis, which is actually a calculational method, you can present a next task to a student, which takes into account the efficiency of the schemas in terms of the performance and mental effort. We have also used that to get an impression of motivation of the student, like we just saw on this last problem. So if you have high performance with high mental effort, then you know that the student was motivated. On the other hand, if you have low performance with low mental effort, like we just saw, that means that the motivation is low, and you can adjust your the examples that you present to the learner based on that. So based on that, you can categorize learning tasks into this scheme and present them or respond to them in your adaptive learning system. We have done this in several adaptive learning systems, and we made one for the training of air traffic controllers, and you can see the algorithm that we used here, which is actually very simple. So basically, the tasks are chosen from a database based on their performance and their mental effort. And so, for instance, if the performance was 5 on a 7-point scale, which is high, and the mental effort was, let's say, 2, which is low, then the student will get a problem go 3 steps up. And 3 steps up can mean that they will get a different problem type with less guidance, or they might go to a higher complexity level. And that's you can define this in the system. It's actually a simple system, but in our studies show that the air traffic control trainees who use this system perform better than the trainees who used like the fixed sequence, the sequence they normally use in the training. So far for the fixed and adaptive sequences. Are there any questions on that? So otherwise we will go on to the next. Okay, and go on. So during my keynote, I mentioned the relative age effect or the birth date effect, and we saw that it could have rather decisive consequences. So like it was shown in this picture, that someone who was born in September has 30% less chance of being a first graduate of Oxford than someone who was born in August. And so we saw that this is based on what happens actually when children are young in school because of the cutoff date. And so the children that are young in a classroom are less developed from a cognitive point of view, but also from a physical point of view. And teachers normally or often identify this as being less talented. So my question to you is, well, what could you do about this problem? It's a problem that doesn't already exist for a long time, so you would expect that it would already have been solved, but it's still a problem. It's still the same problem, I think. So does anyone have an idea what could be done to solve this? Yeah, I cannot hear you.
I don't have an idea, but I just want to check, Prof. Are you saying it has a
successful you are in life. Is that what you're saying? That the month you were born in has a decisive influence on how successful you are in life.
Yeah. Yeah.
So is that a true concept? So if I was born in December, then I'll be successful?
Well, of course, this is an average. Like, of course, if there are also many people who are the youngest in class and are now very successful, but as everything, like the average outcome of this is that if you are the youngest in class, then on average, like you can see here, it's clear that they looked at a lot of students, and it's also in sports, like it's in almost every sport where physical performance and cognition is important, you see the same effect. And it's also like for instance, in the Netherlands, the school year starts in September, but I think in Australia it starts in January. And so you see, also based on that, in Australia, the people who are most successful are born in January, February, whereas in the Netherlands, they are the people who are born in September.
That's why I have a problem with that. I think it's contextual because, as you rightfully point out, people start school in different countries at different ages and at different times. But I want to say, yes, I agree that during school years, if a school begins in January and somebody who was born in July is in the same class as those born in January, developmentally they are behind, but eventually they catch up. So we can't say they are less successful simply because they were not able to hold the pen the same way as those who were born in January at the beginning of the year. By the end of the year, they would have caught up. Especially by the end of the school year, they would caught up and things level out. So I really don't agree with the statement that in life, I can understand when you are saying during school, those born in years, I mean those who are half a year old younger than others will be developmentally behind. That I agree with. But to say those born in certain months are more successful than others,
Yeah, but this is not just an idea. It's based on facts. So it's not an idea. It's yeah. So yeah. Yeah. And that might also be a problem that people think that this is not really a problem, or that it will even out after a year or maybe a few years. And that might also be a problem why no one does anything about the problem. Yeah, because if you say that it evens out, then you should be able to explain why you see it in top sport and at the university level, because then it should already have been gone, or if you. Yeah. Yes.
Thank you. I'm just following up on that. So in terms of these findings of this study, what is the role of context, in that? Because probably we argue it because from where we stand, from where we come from, I would agree with my colleague that I wouldn't agree with the study. So my question is to you, is this a universal finding that to say it's facts? It's facts for who, in which context, and what was the role of the nature of the development of that particular cohort of participants that you used?
Yeah, if context would play an important role, then it would not be visible. Like you would not see that was such a big difference, and it's and you can find it like everywhere, for instance in sports, and also in education and like society. It's a general phenomenon that has also been shown in China, in the United States, in Europe. I'm not sure whether it has been shown in other. Yeah. Yeah, maybe that's the case. I haven't seen that. Yeah.
Yeah.
Yeah, that could be. Yeah. Yeah.
But another thing, Prof, maybe let's just check here. How many people were born in January here? How many people were born in January? So we've got professors that were born in January. Feb, thank you. March, April, May, June, July, August, September, October,
Oh, well, you see.
November, December. So every month is represented here, and it's not even the full house that's here, you know. And remember, people born in September were conceived at Christmas during those holidays. So there are more people born in September than in any other month because of the holidays, you know. So honestly,
what did you say? I don't know. Yeah, I cannot hear you from here. That's all. Okay, so for like, I still haven't heard a strategy that can be used to prevent this problem. Yeah, so you say that those are younger, need more motivation and more teaching. Yeah. Yeah. We could not hear you, sorry.
Heckman's research, he has done a longitudinal study for 20-25 years and then showed that how they study in early childhood actually decides what they do in future. So is there any connection with that? That I'm just trying to, see is there any reason why this kind of R square with a decent number? Heckman's equation.
What was the question?
No, I'm just trying to understand. Yeah. So Heckman has done a longitudinal study on early childhood children, like pre-primary children, and then he has actually found that those who have put in a lot of effort during that early childhood days, actually they generally do well. So is there any connection with that? I'm not able to understand.
You mean if they put more effort into early childhood education?
Yeah, in terms of
Yeah, I don't know, because I don't think that happens. Like this happens when children enter primary school, and so that's where it all starts. And maybe even before, if children are in a sports team, then they will also be the children that are already like 10 months older. They are identified as more talented. They get more positive feedback from the coach. Get better training, better training environment. And that's how it works. Also in education. Although teachers don't recognize this because of the fact that they confuse this with the talent, like the developmental age. Yeah. So I think if teachers are aware of the problem and don't deemed, I think they should be aware of the problem. And then they could, they could use the month, especially in the first classes when the child was born, and to give them maybe the same feedback as other children. So you give every child the same feedback.
Fred? He can't hear me.
Hello, we were just discussing on your question of how could you address this. And just before this, you showed the efficiency and involvement matrix, like a graph. Could you take the data from here and apply it to that particular matrix in order to address the imbalances that shown here?
Yeah, I would say that like if you have your younger children in the classroom, they perform worse, and they need to invest more effort than the children that are older, that are more cognitively and physically developed. So the children who are older will do better. So if you recognize this higher performance and less effort as being more intelligent or more talented.
Would that be a workable strategy? Because you're asking about think of strategies that could be used to manage this cognitive load. I mean, the question on the slide I'm talking about. And would that be an appropriate strategy to use, utilizing the matrix that you had shown, the graph earlier with?
Do we need to go back in this slide?
No, go back. But just using this data, because you're trying to address the
but if you would use that, you still don't take the month of someone was born into account. So if you just look at performance and mental effort, then you would still say that someone is less performs less well and might be less talented or intelligent than the other.
And you wouldn't address these inequalities that's already shown by month-wise.
That is of course possible. If you would divide the students by month, then that would be a good strategy to do. But then you need to be aware of that, and you can adjust your instruction to that. I'm not sure. I think it would work, but it has not been tried. Okay, let's close this topic and go on to the next one. Oh, we should have to stop? Okay. Then I will stop now. Okay, thank you for your attention. Yeah.